Hi, my name is AlleyBorden, and this is my legacy project. And I'm going to be doing problem 4.22 from Griffiths. And I'll go ahead and read that. It says a very long cylinder of linear dielectric material is placed in an otherwise uniform electric field E0. Find the resulting field within the cylinder. The radius is A, the susceptibility is chi sub E, and the axis is perpendicular to E0. So to start, I'm going to lay down a few boundary conditions that I've gotten from the book, the equation 4.43. And the first one is that the potential on the inside is equal to the potential on the outside when the distance is equal to the radius. And our second boundary condition says that epsilon times the derivative of the potential with respect to the distance is equal to epsilon naught times the derivative of the potential on the outside. And our third boundary condition says that the potential on the outside goes as E naught times the distance times cosine theta for a distance much greater than the radius. And then from condition 1, these are the equations from previous work. These are the equations for the potential on the inside, summed over all space. It's radius raised to the power of k times a constant times cosine k theta plus a constant times sine of k theta. And from the potential on the outside, we have the sum over all space, the radius raised to the negative k times a constant times cosine of the angle plus constant times sine of the angle minus E naught times the distance times cosine theta. Then from condition number 2, we're just going to take the derivative of those two functions. And we include the permittivity factors. And then from condition 3, we said that the potential is equal to E naught times cosine of the angle plus this summation, whereas S gets really large, this all goes to 0. And so based on that, we're going to, for all values of k, as S is taking this term to 0, we get these two constants are equal to 0. That's B sub k and D sub k. So then we're going to plug in a 1 for k based on condition 1. And then we're left with a to the power of k times constant cosine of the angle equals negative E naught times the radius times cosine of the angle plus a to the negative k times a constant times cosine of the angle. We're going to plug in our 1. We're left with all cosine thetas, so those can all cancel out, and then our equation reduces to this right here, where we just have radius times a constant equal to negative E naught times the radius plus radius raised to the negative 1 times a constant. And then from condition 2, we're just going to take that derivative of this equation and we're left with epsilon sub r is equal to negative E naught minus a to the negative 2 times a constant. And then from Griffiths, I use equation 4.34 that states that epsilon sub r is defined to be 1 plus the permittivity, or I'm sorry, the susceptibility, and that's equal to epsilon over epsilon naught. So after plugging that in, we're left with our constant A sub 1 is equal to negative E naught over 1 plus the susceptibility divided by 2. And from there, for the potential on the inside, we just include this cosine term. We say cosine S times cosine theta equal to X. And then our potential is given as negative of E naught times X over 1 plus susceptibility divided by 2. And then for our final answer, we just have the E field on the inside is equal to E naught over 1 plus susceptibility divided by 2. And that's all I've got. Thank you.